Hello, my name is Paul Adams. I'm a student in the Master of Science in Data Science program at Southern Methodist University in Dallas, Texas. In this video, I'm going to discuss multi-head attention, which is used to capture context and meaning for sequence transduction learning. Multi-head attention is a mechanism used to learn simultaneously from multiple subspace representations within sequenced data. I will present this topic within the context of the transformer model architecture, a model that popularly uses multi-head attention in an encoder-decoder process to enable models such as the BERT and Universal Sentence Encoder to learn using natural language. This presentation assumes prior knowledge of feed-forward neural networks and how they work to map inputs to outputs, such as the application of weights and bias terms, scaling and normalizing, dimension reduction through linear projection, backpropagation, regularization, and obtaining target probabilities using softmax calculations. Our approach in this presentation is to focus primarily on the processing of information into and through the multi-head attention mechanism and the implications that has on downstream tasks. First, we'll begin with a high-level overview of attention, recurrence, and convolution. Next, I'll give an overview of the transformer architecture, which uses multi-head attention for sequence transduction modeling. After, we'll discuss positional encoding and how this enables attention to work. Then I'll give a deeper explanation of what attention within the transformer architecture is, followed by what multi-head attention is and how it's different than single-headed attention. And finally, I'll explain the ways in which the transformer architecture implements multi-head attention to accomplish sequence transduction learning. Attention-based models use parallelized computation on fixed scales to gain context from global intra-sequence dependencies. In other words, the first word in a sequence has the potential to be as influential on the meaning and importance of the last word in the sequence as the second to last word does. Except for in very short sequences, this is not practical to assume for other models, such as those using recurrence and convolution. Precluding attention-based modeling are recurrence-based models, such as the recurrent neural network, long short-term memory, and gated recurrent unit. The primary issue with these recurrence-based models is the dependency on positional distances to capture context. Within recurrence-based networks, the order of word occurrence in their sequences is crucial. Where the closer surrounding words are to a given word, the more likely those words will influence the contextual understanding of the given word. These models are great for short sequences, but as the sequences grow in length, contextual understanding similarly declines, resulting in misinterpretation and other products of loss. Perhaps more similar to attention than recurrence is the character-based convolutional approach. However, as with recurrence, convolution encounters similar issues of distance calculations that recurrence-based models do, reducing performance and speed as sequence lengths increase. As with attention, convolution uses a signal-based approach to learning context from natural language. In a moment, I will explain how attention uses these signals as an underlying method for capturing sequence ordering, but for now we will focus briefly on convolution. Consider how words co-occur in similar frequencies, with similar distances, within a given language, for example, English. In the phrase, I am going, the verb go carries with it the present participle ing, to form a gerund, which can be followed by the preposition to. If first person, the preceding pronoun is I. Therefore, convolution learns that I can often be followed by am, and then followed in turn by going to. After this, the next word in a sequence could be graduate, completing the phrase I am going to graduate, which a convolutional approach can quantify and feed into pooling and softmax layers for classification as a positive sentiment. This example provides language at the word level. However, because distance is important for convolutional models, it is also hindered by longer sequences. Additionally, because the character convolutional approach focuses on character level learning, it is not robust to changes in pattern, such as misspellings or infrequent grammatical usage, and is thus more prone to overfitting and requires larger training corpora. To help explain attention and multi-head attention, we'll look at it through the context of the transformer model architecture. The transformer is a model commonly used in natural language processing that leverages attention to capture global dependencies within language modeling and machine translation sequences. Within the transformer architecture, an unlearned input embedding is processed into a positional encoder that works to make sequence order an underlying fact rather than something attention must maintain focus on. The output embedding is also processed through a positional encoder, but shifted to the right. The transformer uses attention to provide context to words to derive context vectors used in downstream feed-forward layers, which measure context similarities across distributions of sequences. Output embeddings from that feed-forward layer are concatenated and normalized, then processed into the decoder. Once in the decoder, the output from the encoder is mapped using queries from the decoder's own contextualized vocabulary to provide translation as the target output, which is then processed through an additional feed-forward layer prior to being linearly projected and processed through a softmax layer to provide output probabilities. Positional encoding is the relative positioning of words belonging to sequences along geometric progressions of those sequences, executed by assignment of odd and even words to cosine and sine functions, respectively. The encoding is important because the transformer model does not have a sense of order and position, since directionality is not directly considered, but a sense of order and position is still required. Positional encoding adds that information by creating a word position signal based on the sine and cosine functions, which in turn provide the model framework with a pseudo-ordering functionality. Because cosine functions reach maximum amplitude before sine functions, odd words are assigned cosine encodings, which begin with the first index of sequences. Therefore, because sine functions reach a maximum amplitude after cosine, but before cosine peaks again, sine functions are assigned to the even words. These two functions are selected because they have the same frequency and periods. As additional words are added to the odd and even positions, these words progress along the domain from 2 pi to 1000 times 2 pi. In sinusoidal encoding, the distance between the words, which are treated as linear continuous time steps, are symmetrical, which decay smoothly with time. This is useful for maintaining contextual attention as it scales well with time complexity and therefore enables the model to maintain more global contextual comprehension than if the time steps were integer-based. The attention used in multi-head attention of the transformer architecture refers to scaled dot product attention. To be clear, attention functions are applied to sets of queries in parallel. The method uses the dot product of query matrices and corresponding key matrices to provide weighted sum context vectors of original word sequences. When applied to natural language, the query is the word in the target sequence, the key is the word used, and the value is an original encoded representation of the keyword. After query matrices are multiplied against the transposed key matrices to derive context vectors, output is scaled using the square root of the shared dimensional value of the keys and queries matrices. It's important to note that a scaling value is applied to the context vector to prevent the softmax function from returning diminutive gradients, which can quickly result in overfitting. The next part of the process is the application of the softmax. The softmax generates a target probability distribution, which is then multiplied against the values matrix. The result is what is called the scaled dot product attention score. In multi-head attention, this operation is performed multiple times in parallel, where each attention score is obtained from different learned linear projections of keys, queries, and values. The scores themselves are then concatenated and processed into a linear projection from a multidimensional space. When using only one attention head, averaging prevents attending to information from different representation subspaces at different positions within each sequence. In multi-head attention, multiple attention heads are used to circumvent this constraint. To restate the underlying purpose of multi-head attention and why it is different than single-headed attention, multi-head attention allows models to learn different contextual representations from the same sequences and use all context gained to obtain the most representative contextual representation once passed through the softmax layer. In the transformer model, multi-head attention is implemented with three different objectives. The first implementation of the multi-head attention mechanism is in what is referred to as the encoder stack. Here, input embeddings are learned within a multiple self-attention layer before processing through a feed-forward layer. In this implementation, the keys, queries, and values share the same origin, which is the output of the positional encoder. This enables the encoder to attend to all positions in previous layers of the encoder. This means that all words previously used can be reused to assign context to the next word. The second implementation of multi-head attention is in what is referred to as the decoder stack, where learned embeddings from the encoder are trained. The second implementation is the masked multi-head attention layer. Because attention does not directly attend to ordering within sequences, there is a risk of data leakage. Also referred to as leftward information flow, this leakage corrupts the autoregressive property needed for attention scores to be used in providing predictions. Simply stated, the autoregressive property refers to the attention mechanism only learning from prior words in the signal and not those in the future. To accomplish this, values are masked with negative infinity in the softmax input that correspond to illegal connections, or those connections that exist in the future. In other words, masking prevents the attention mechanism from regurgitating future words in the sequence based on an attention's disorientation with respect to sequence order, and instead forces the model to provide non-leaked predictions. The third and final implementation of multi-head attention in the transformer model also takes place in the decoder stack, but it is a combination of the encoder and decoder values. For this reason, it is referred to as the encoder-decoder attention layer. In this process, queries come from the previous layer, following masked multi-head attention, while the keys and values originate from the encoder stack's output. This encoder-decoder architecture is integral in sequence transduction models. The encoder provides the keys and values so the decoder can map those values as input to find the most similar values in the decoder's vocabulary and provide those values as the target output. In summary, multi-head attention provides a method to learn from different representative subspaces of sequenced data without directly storing ordering in memory. This provides a method for learning from longer sequences of data with less overfitting, less memory dependence, and higher processing speed. Thank you for your time.